Okay, welcome to the final certification training for nutrient management planners web series seminar. This week we're going to be talking about the phosphorus loss assessment tool. If you'll give me a few minutes, I need to cut and paste some information for you into the text box here for you. Oops. There we go. Basically what I'm trying to provide you here is some information about where you can go to download the slide set if you haven't already done so. So as I've said in the past few weeks, to get the most out of this presentation, one of the things you might want to do is have the hard copy of the slides in front of you, and you can get those off of the Moodle course website with the link that's provided to you there. You'll need to log in with your username, password, download the handout, and then you can resume the playback of this presentation. Now, another thing is that since you're listening to this recorded, you don't have the benefit of being able to interact real time with Dr. Osmond during the presentation. So if at any time you have questions about the material you're learning here today, just send Dr. Osmond an email at the address provided there in the dialog box. And with that, I'm going to turn the program over to Deanna Osmond, and she's going to talk to you today about the phosphorus loss assessment tool.
Thank you, David. If you all remember back when we were talking about the USDA NRCS nutrient management standard, one of the aspects of that standard for anyone that applied nutrients that came from organic sources was they had to run some type of phosphorus index. And back then we told you that we would talk more specifically about that phosphorus index in a couple weeks. The name of the phosphorus index that we use in North Carolina is the North Carolina Phosphorus Loss Assessment Tool, which we call usually PLAT as a shortened name. And so what I would like to do today is a twofold lecture. The first part of the discussion will be how the phosphorus loss assessment tool works. And the second part of the discussion will be how you actually implement the phosphorus loss assessment tool. We found after the tool was developed and folks started using it that different people were using it in very different ways, and so we want to try and standardize how it's actually used in the field. And with that, we'll begin. When NRCS developed its nutrient management standard, its 590 standard, it gave each state the right to choose 3 different ways to determine phosphorus losses or phosphorus cutoff. One was a soil test threshold, and basically what that says is that you simply, if you get to a certain soil test level, you cannot apply any more organic material that contains phosphorus. Another is an environmental threshold, and the third is a site-specific phosphorus loss assessment or index. That is what North Carolina has chosen to do, is use the site-specific loss assessment or index. There was an existing model that was the prototype for all the phosphorus loss assessments. It had weighted parameters by the importance of phosphorus loss, and I'll give you an example of this, so if these words don't make any sense, don't worry, we're going to go over this. They assigned each parameter a value based on the conditions of the site, and then they multiplied the weight times the parameter to get an overall assessment loss. 3 of the 50 states chose to use just a soil test phosphorus level to cut off the additional application of primarily animal waste, but it could be organic materials. The rest of the states use different form of phosphorus indices, and some of these states use a combination of a phosphorus index with also a soil test threshold cutoff. For instance, Indiana, I believe, has a soil test threshold cutoff of around 100, as well as a phosphorus index. So every state did it a little bit differently, but what we want to do is focus on North Carolina. Now, the original phosphorus assessment index was developed by a gentleman by the name of Lemunyon who worked for NRCS, And they basically went through and they said, what are the important factors that transport phosphorus from an agricultural field into a water resource? Soil erosion, obviously. Soil class is important because soil class determines how much runoff you have. So basically, soil runoff class is a surrogate for the amount of soluble phosphorus loss. Soil test phosphorus is important. The amount of phosphorus that you put on from fertilizer and the way you put it on are important. The amount of phosphorus that is added through organic materials and the way you put that on are also important. They then said each of these should have a different weighting factor. How important is that property as far as off-site phosphorus loss? And they said, well, erosion is the most important, so we're going to give it a weighting factor of 1.5. We think actually phosphorus fertilizer rate and the application way you put it on are the least important. So they gave fertilizer phosphorus rate and application method the lowest weighting factor. They then divided the losses of each of the properties into either none, low, medium, high, or very high, and assigned a numeric value to each of these rankings. So if you have low soil erosion, for example, and let me get my little sign here. If you have low soil erosion, let's try this again. If you have low soil erosion, you get a point of 1. If you have very high soil erosion, you get 8 points. And so you go through each of these properties, you assign it a rating number based on the characteristic within the rating categories, and then you multiply that number, so in this case it would be 8 times 1.5. And you go through for each property and you multiply whatever the rating is by the weighting factor, and then at the end of the day you add these up. The problem is, for North Carolina, we have extremes in our climate, extremes in our topography, extremes in our soil types. There's nothing uniform about the agriculture in North Carolina. So we have the greatest change in elevation along the Atlantic coast from sea level up to Mount Mitchell, which is almost 7,000 feet. So we've got huge topographic changes. We have 6 physiographic regions: the mountains, the Piedmont, the sandhills, the intercoastal plain, the outer coastal plain, and the coastal islands. They each have not only unique topographies, but soil, climate, and vegetation. Further confounding this diversity in lands in North Carolina, we have different kinds of agricultural systems. So let's start with the mountains that has really complex agricultural systems with lots of different crops. A lot of vegetable crops are grown. In the lowlands near the rivers, we have Christmas tree production in the mountain slopes, and we have some dairy in the region. We then go to the Piedmont, which has iron and aluminum rich mineral soils with really complex soils. There's some row crops, but the most dominant crop in this area is actually pastures and hayland. There is a lot of poultry produced in this particular region, as well as some dairy. And so here's a picture of those pastured situations that we see throughout this region of North Carolina. In addition, we have the coastal plain area, which has lots of different types of soil, some of which developed from marine sediments. They are anywhere from excessively well drained to poorly drained, depending on the katina that they're in. Oftentimes the surfaces are fine loamy sands, and occasionally you'll have clays. We produce everything from row crops to vegetables to forages. And a lot of these soils is where the swine lagoon effluent is applied, because the majority of the swine production is in the coastal plain of North Carolina. A recent event with the arrival of a large swine industry has been permanent hayland going into coastal plain soils. Typically there wasn't much hay in the coastal plain, it was primarily row crops, but the swine industry has changed this. As we get closer to the ocean, our coastal plain soils can become very wet. Some of these soils are very sandy, and in order to be productive, they require regular spacing of drainage networks. There are some lagoon spray fields on these kinds of soil and also poultry application, but typically the closer you get to the coast, the less animal agriculture you see. In addition to finding sandy soils, you can also find mineral organic soils. These tend to have fairly large amounts of organic materials, and they're typically overlain by shallow groundwater systems, and so it provides the need to drain these soils on a fairly regular basis. The most eastern physiographic region of North Carolina has deep organic soils. These were basically swamplands that formed organic soils. They have to be drained to be productive, and primarily row crop dominates these systems. There's very little animal waste applied to these organic soils. So soil systems, as you can see from this map, are highly variable in North Carolina, and they reflect not only geographic variation of climate, vegetation, and geological processes, but also the different kinds of soil systems. And so you can see that we have a lot of distinct soils in North Carolina, and specifically we have almost 500 soil series in North Carolina that consist of anything from sands to organic soils. On the coastal plain, we tend to have loamy sands, Piedmont, acidic, mafic, slate belt kinds of soils, and the mountain floodplains. Mountains have floodplains with some, oftentimes with slopes. We also have a range of animal types in North Carolina. Dairy, which primarily spreads slurry or scraped materials. Swine, which either has lagoon effluent or slurry, which is primarily the sludge. And poultry, primarily litter, but for some poultry layer operations, we have lagoons. Sometimes these materials are surface applied, sometimes they're incorporated, sometimes they're injected. It just really depends on the type of material that the producers are working with. So again, we have a great deal of variation in North Carolina. The reason I talk about this variation is that we were really concerned about using the national P index. We wanted to have a better sense of how the phosphorus actually leaves our systems in North Carolina because they are so diverse. We also wanted to know what were the site-specific factors in any given field that control phosphorus loss, and are there conservation practices that can prevent these phosphorus losses. If you flip back to the National Phosphorus Index that was developed, you'll see that there are no conservation practices really to prevent phosphorus losses, or even management, different kinds of management that you might use to affect phosphorus loss. And so we wanted to develop an index that was more robust. We wanted to be able to look at particulate losses of phosphorus, that is phosphorus attached to soil particles. We wanted to look at soluble losses of phosphorus, that is phosphorus that's in the soil can be released from the soil as water runs over it. And so we wanted to be able to pick up those phosphorus losses. We know in North Carolina in particular situations, typically these are extremely sandy soils with large applications of animal waste, particularly swine effluent. We get phosphorus leaching through the soil, And I think we showed you a picture of that when 2 weeks ago when we were talking about how phosphorus moved. And last but not least, we want to capture the source losses. This would either be fertilizer that's put on the soil or mixed into the soil, or manures that are put on the soil or mixed into the soil. These source losses occur when water runs off the soil from the field into the water resource of concern. So this is a runoff pathway, but we wanted to separate the source loss pathway from the soluble phosphorus released from the soil. We consider the source, we consider the transport, and we consider the conservation practices that are used. We want to address it in a quantitative way, and we're going to talk about how we do that. The entire time we were developing this tool, we pulled the very best quantitative numbers we could, and if there were certain uncertainties about the numbers we were using, or we didn't have particularly good numbers, we always chose to be environmentally protective. So let me talk exactly about how we developed PLAT, each of the 4 pathways. So the first pathway I want to talk about is the particulate phosphorus loss. That is the phosphorus that's attached to soil, and then the soil erodes from the field. We need to know 2 things. How much soil is eroding? What is the soil test phosphorus? The soil test phosphorus gives us the concentration. And then what conservation practices are we using that will actually reduce that phosphorus loss from the field? So we're considering source. So source is the soil test phosphorus. We're considering transport, that's the erosion part, and then the conservation practices. This is some work done by Dr. Cox in our department, and it's really important work. This concept is a little tricky, but it's critical to understanding the rest of what we're going to do. On your y-axis, we're showing you the relationship between what you get out of your soil test analysis as you add 1 unit of phosphorus. So you can think about this: if we add 1 unit of phosphorus, how much additional Mehlich 3P are we going to see from our soil test? We need to look at the amount of clay to determine this ratio of Mehlich 3P or soil test P to phosphorus added. At 10% clay, so these are pretty sandy soils, we see that for every unit of phosphorus added, the soil test phosphorus will increase by 0.7. So it's not 1-to-1. The soil is sorbing some of that phosphorus, but not all of it. As you go down to a very clay soil in North Carolina, 40%, you see that for every unit of phosphorus added, you only have a Mehlich 3P of 0.2. What this tells us is that at the same soil test phosphorus, you will have considerably more phosphorus in your clay soil than you will your sandy soil, because the clay soil is absorbing much of the phosphorus. And so that's really important as we think about our soil test P concentration levels vis-a-vis the amount of phosphorus in those soils. So we could take this relationship that Dr. Cox built about the amount of phosphorus in a soil relative to Mehlich 3P, and we came up with this total P factor in pounds per ton. So for every ton of sediment eroded, we have this relationship for pounds of P per ton versus Mehlich 3P. So maleic 3P is in milligrams per kilogram. This is a little different than you all normally see it. Typically, you see it as phosphorus index, but they're reasonably close in approximation. And so what this tells us is that at a maleic 3P of 100, if you have a clay soil, you're going to lose 2.5 pounds of phosphorus for every ton of soil that you lose. Because as you remember, at the same soil test phosphorus level, clay soils have a lot more phosphorus than sandy textured soils. If you have a soil that only has 10% clay, and it has a maleic 3P of 100, you're going to only lose 0.2 pounds of phosphorus per ton. Where do we get the most erosion in North Carolina? It's on our more clay texture soils that tend to contain more phosphorus. And so by knowing how much soil we're losing, knowing the approximate clay concentration of our soil, which we get from our soil mapping unit, the North Carolina Plat program determines automatically how much phosphorus is lost from erosion. Now the nice thing for you, the user, is that all you need to know in order to calculate this is what county you're in, what your predominant soil mapping unit is, and what your erosion rate is. You will obtain that erosion rate from your Russell II calculation, which you'll learn to do during the nutrient management training. You don't need to know what your clay percent is because it's calculated for you automatically from a very large database. So we have our erosion. We have our concentration, which is our soil test P. The only other thing we need to look at is our conservation practices. The most effective conservation practice we have that is off the field is a riparian buffer. Now, there are conservation practices that you can use to reduce your erosion, but those are separate from actual conservation practices that you have that are off field. So when you look at the effective buffer width on particulate P delivery, you see the buffer P delivery ratio on the y-axis and the buffer width in feet on the x-axis. If you have no buffer, it says that 100% of that attached phosphorus will be delivered to your water resource. If you only have 15-foot riparian buffer, you will only deliver 40% of the phosphorus attached sediment. This means that 60% of the phosphorus is not delivered to the water resource. Now, when we talk about buffer widths, we don't really care what the vegetation type is, but we are assuming that you get sheet flow across the buffer, that you aren't having problems with concentrated flow delivery. So we don't care what kind of buffer you have. At 50 feet, you get about 25% delivery of the phosphorus, and you have close to 75% retention of that sediment-bound phosphorus within the buffer. Clearly, your biggest bang for the buck is your first 15 feet of buffer. And buffers occasionally have to be maintained to assure that the sediment doesn't build up over time and short-circuit the buffer. So we have a couple other practices that can reduce sediment-bound phosphorus. Water control structures deliver 65% of the phosphorus. That means they retain 35% of the phosphorus. A pond will deliver 30% of the phosphorus, or it will retain 70% of the phosphorus. And when we talk about ponds, we're talking about structures that have, they may have a channel going into the pond, but typically they don't have an outflow channel. They may have an emergency spillway, but it's not an inflow-outflow situation. Typically, these are ponds in the Piedmont that were built for either irrigation for tobacco or drinking water for cows. When we talk about a sediment basin, we're talking about a basin that has a stream flowing in and a stream flowing out. We think that they only trap 10% of the phosphorus, and therefore they deliver 90% of the phosphorus. So they're not particularly effective because the phosphorus just flows in and then the phosphorus just flows out. So we only have 4 practices that actually reduce sediment-bound phosphorus. So the next phosphorus pool that we want to talk is the loss of soluble phosphorus. We need to know the runoff volume from a soil, and then we need to know the soil test piece. So we know the concentration and we know the amount of runoff. And if you know these 2 things, then you can determine the amount of phosphorus that's leaving the soil. Runoff volume is fairly tricky because it depends on lots of different factors. It depends on the soil properties, whether or not you have drainage, what kind of cropping system you have, and of course the cropping system can greatly affect your residue management. And then if you have, then you need to know your local long-term weather data, because it's weather that actually drives the amount of rainfall and the intensity of rainfall and determines to a large extent the amount of water that runs off. Again, we have these kinds of relationship between runoff in parts per million or milligrams per liter. So we're looking at the amount of phosphorus that runs off, and the soil test index. And again, as you're increasing your soil test, you're also increasing amount of phosphorus that runs off. And we can see this more clearly when we look at not only runoff losses, but phosphorus concentration. The y-axis is the phosphorus loss at the field edge in pounds of phosphorus per acre per year. The soil type is in the x-axis. We have very sandy textured soils here and going into loamy soils. As your organic matter increases, the amount of phosphorus that you lose through the soluble processes increases dramatically. These soils out here are your organic soils. This is data from Gilliam and Skaggs. That's because you have considerably more runoff on these organic textured soils than you have on your sandy textured soils. So the amount of phosphorus that runs off is also a function of the runoff capacity of these soils. Again, Dr. Cox did some excellent work looking at the relationship between dissolved phosphorus, milligrams per liter or parts per million. You can use it either way. And the relationship between dissolved P, soil test phosphorus, and soil texture. So basically, Piedmont soils, we're looking at clay textured soils. Coastal plain soils, we're looking at sandy textured soils. On Piedmont soils, you're not losing very much soluble P. And we usually think of the cutoff for loss of soluble P at 1 milligrams per liter. The only reason we set it at 1 milligrams per liter is that that's typically what the wastewater treatment plants are allowed to discharge. If you remember from our first discussion, we talked about phosphorus affecting water quality at concentrations of 0.01 or less. And so clearly 1 milligram per liter is considerably more than the environmental threshold, but we're assuming that there's dilution. And so with a clay textured soil, you don't reach this 1 milligram per liter because the phosphorus is bound very tightly until you reach a Mehlich 3P of about 500. However, in coastal plain soils, you reach this much more quickly. This is about 250. I'm sorry. For the clay textured soils, we're not even reaching it yet. Here's your 1 milligram per liter. And for your sandy textured soils, it's around 250. We took these data and we worked them into algorithms for organic textured soils, it's the square, sandy textured soils, the circle, loamy textured soils, the triangle, and Piedmont textured soils, the diamond. And again, here's our 1 milligram per liter solution phosphorus. And for organic soils, we reach this at a soil test of about 50. For our sandy textured soils, we reach 1 milligram per liter soluble phosphorus loss at 100 Mehlich 3P. For loamy textured soils and also mineral organic soils, as well as shallow organic soils, we reach the 1 milligram threshold at a soil test of around 200. And for our clay textured soils in the Piedmont Mountains, we reach the 1 milligram per liter at a Mehlich 3 of 500. And so these soils have very different soil test thresholds for soluble P loss. So we can relate the amount of soluble phosphorus loss based on our soil test P, but now we need to know how much runoff we have. And we calculate the runoff using two different approaches. The first approach we use is the modified curve number. The gentleman in bio and ag engineering did this part of the work. You need long-term climate records. You need a model that uses the curve number. It uses daily time steps for antecedent moisture, and it calculates daily runoff values for different types of soils depending on their hydrologic group. The most important thing you need to know about this slide is that there are two approaches to estimating runoff. One is for our non-drain soils, and our non-drain soils use this modified curve number approach. The second method we use is through DrainMod for artificially drained soils. And this is the methodology that's used to calculate runoff volume when your soils are drained. We need to determine the drainage index, and this is done through the equation you see here. This factor you don't need to worry about. It's the movement of water through the soil. It's a function of the soil mapping unit, and once you tell us what the soil mapping unit is, this number is picked up in a data table that stores these values. What you do need to know, however, to calculate the drainage index for your particular field is the estimated drainage depth in feet and the distance between drains. Now, typically, in most of our regularly drained systems, that's 300 feet. The depth for draining, for your drainage ditch can be anywhere from 2 feet upwards of 4 or 5 feet. So you put these numbers into the program, and it automatically calculates this drainage index for you. The gentleman in bio and ag engineering developed a series of these curves. They're called French curves. They were based on rainfall in different counties and different cropping systems. This one happens to be from Wilson County, where the rainfall on average is 45 inches per year on a pastured hay situation. The annual outflow in inches, and then the drainage intensity in feet per day. So if we want to know how much water flows overland, it's these black squares. If we have a drainage intensity of 1, we're losing about 1.5 inches of rainfall each year through overland flow. So this is our surface flow. At a drainage index of 1, we are leaching, we are draining almost 13 inches of water per year. So when you look at the amount of water that goes overland versus the amount of water that drains, we have a much higher proportion of water that's draining through our soils than we do going across the surface. So this curve allows us not only to calculate how much runoff volume we have, but it also allows us to calculate how much drainage volume we have. So we know our drainage volumes, we know our phosphorus concentrations, and we can calculate our surface runoff losses. But we just talked about how we could calculate leaching or drainage volumes. And so our third loss pathway is subsurface phosphorus leaching. Now, I need to say that if you're in the Piedmont or the mountains, this equation doesn't even work because we just haven't seen phosphorus leaching very much. Even when we have soil test phosphorus levels of over 1,000 in the mountains in Piedmont, we see almost no phosphorus losses to subsurface systems. And so this subsurface leaching algorithm works for coastal plain soils. So we calculate the drainage volumes. You've seen how you do this using drain mod. We also do it using curve number, and we multiply it again by the soil test P. And again, we use those same relations that I showed you earlier between runoff losses of phosphorus versus soil texture. This is just a graph to show you how much phosphorus actually can be lost in different kinds of soil systems. Both of these soils started out around 250 Mehlich 3P, and as you look at your soil depth in centimeters, going from the top of your soil down to 120 centimeters, and so for those of you that think better in inches, this is about 50 inches down here. You'll see that the sandy textured soil, as you move along the curve, definitely leaches more phosphorus than the clay textured soil. Likewise, the longer you put animal waste on these soils, the more likely you are to leach phosphorus into deeper zones. We have seen phosphorus levels at 30 inches as high as Mehlich 3P of 300. So that's more than 6 times at 30 inches what you need to grow a crop, which means that soil has extraordinarily high amounts of phosphorus stored in it. One of the things about the subsurface leaching is that if you are on a sandy textured soil, you will have to get a soil sample at 30 inches, and we'll talk about that a little bit later. It will require that because that's part of the calculation. The last loss pathway is the source loss of phosphorus. Again, as I said earlier, this is a runoff pathway, but instead of dealing with the phosphorus that's already in the soil, it deals with the phosphorus that you're putting on the soil. We need to know how much phosphorus you're putting on the soil. So that's the total P per unit factor. We need to know how much of it you're putting on. Are you putting on 1 ton of broiler litter, or are you putting on 5 tons of broiler litter? How are you putting this on? Is it surface applied? Are you disking it in? We'll talk about the mobile P fraction, which is really how much soluble phosphorus is in the material that you're putting on. And then the runoff fraction is simply part of the runoff amount that we've been calculating in the other portions of plat and the delivery fraction. So let's talk about some of these specifics. First of all, there's the application method. If you inject a material or you incorporate the materials, there's less likelihood that you're going to be moving this material off through surface runoff. And again, the source factor deals with surface runoff. If you just apply it on the surface, we're assuming that all the phosphorus that you put down is available to run off. It's not to say that it all will, because it won't. There are other factors that are important, but just the availability to run off. Clearly, if you're injecting it, there's none of that material sitting on the surface. We also want to look at potentially mobile source phosphorus. So we're looking at surface soluble and lightweight surface insoluble. So surface soluble would be things like swine effluent. Most of the phosphorus in that material is very soluble. It's not in a non-soluble form. So a good portion of that would be soluble. There might be tiny little flakes, for instance, in poultry litter that's very lightweight that can float off the surface of the soil. So that's the lightweight surface insoluble that will be lost. But then you have these other portions that will either infiltrate or it will stay on the surface and won't move due to runoff. So one of the factors that we just talked about is this mobile P fraction. And so you can see for broiler house litter, on average, a ton of broiler litter has about 35 pounds of total P. And of that 35 pounds of total P, about 35%, a third of it is mobile. So 35 pounds, a third is mobile. So that's about 12 pounds of phosphorus is going to be mobile. And so if you put that litter on the surface, which most people do, you have 13 potential pounds of phosphorus that can run off. But as you notice, beef slurry is much less soluble than it has a much lower mobile P fraction than the broiler house litter. And so you're interested in not only in the mobile P fraction, but also the total amount of phosphorus. And you'll notice in this slide that dairy has the least amount of phosphorus per unit of application, 1,000 gallons, relative to some of these other sources. So we've discussed each of the loss pathways: particulate losses, soluble P losses in runoff, this is from the soil; subsurface P losses, this is primarily in the coastal plain; source surface P losses, again these are runoff from the sources. We add them all together to figure out our total potential phosphorus loss from this field. We have raw scores that are calculated, but then these are transformed into the North Carolina Platte values. So if we lose 0 to 1 pounds of phosphorus per acre per year, that has a value of anywhere from 0 to 25, and we consider that low. 1.1 to 2, it has a Platte rating of 26 to 50, and it's considered medium. At those two particular Platte ratings, you can continue to apply on a nitrogen basis. However, you have to recognize that in most systems, if you continue to apply animal waste, you will ultimately end up with high or very high. So you need to pay really close attention to these phosphorus loss scores. When you hit high, a high rating, the NRCS 590 nutrient management standard says that you can only apply enough phosphorus for crop usage. And so that means that you will be under applying nitrogen, and you will have to make up your nitrogen from commercial fertilizers. At very high Platte ratings, it means you can no longer apply phosphorus to this field. Typically, when you're at a very high Platte rating, your soil test phosphorus levels are over 200 or above, which means that those fields don't need phosphorus probably for the next 100 plus years. And so Platte ratings are very important to look at because they determine the types of management that you can use. So that's it for talking about how the phosphorus loss assessment tool actually works. What I want to turn to now is how you actually use the phosphorus loss assessment tool, or PLAT, in the field. Because again, as I said, when folks first started using this, there were all kinds of differences in how they were using it. And we want to talk about some of the most frequently asked questions. So the first is, do you plan your nutrient management on a whole field or a partial field? And this depends. You have the right to make this decision of subdividing fields. Keep in mind, however, that most fields in North Carolina, the average field size is 8 to 10 acres. You're going to have to talk to the producers to find out whether they're really willing to manage their fields differently. And if they are, then there's some guidance you can use about how to divide your fields. So this would be true not only for conducting your PLAT analysis, but also your nutrient management plan. First thing is, do you have pretty similar soils? And do these similar soils represent at least 65% of the fields? In North Carolina, you cannot guarantee that. Sometimes there are very large inclusions that are completely different from the rest of the field. So you're the one that's going to have to answer this question, and you're the one that's going to have to recognize the management implications if you do divide the field. So if you have similar soils in your field, do you have similar conservation practices and management? Typically this is true because our fields are so small, it's very unusual to have different kinds of management. If the answer to all these questions are yes, just keep the field together, you don't have to split it up. If, however, the soils are dissimilar, will they have a significant impact on plat, erosion, runoff, etc.? If you don't think so, again, these fields can be managed, this field can be managed as an entire field. If you think there are going to be very significant differences, then you may want to divide it. But again, this is going to have to be a discussion between you and the producer to see what he or she is willing to do. Soil mapping units. This is a question we've often had. People will say, I don't think the soil is actually what it's mapped as. And that's absolutely possible. Dr. Krause has talked to you a little bit about that, so you know how much variation there can actually be separate from the way the field is mapped. So if you think the soil is mapped incorrectly, you can go to NRCS Soils Maps and check the current maps at the field office, or use the tool that David talked to you about last week. You can contact an area resource soil scientist via the field office to try and get your field remapped. Let me just say that trying to get fields remapped these days are extremely difficult because NRCS doesn't have many soil scientists in the field these days. And so you do have this option open to you, although it can be quite difficult. Crop and tillage. Let's talk about how that affects plat. Within the plat program, you will be asked if you have conventional tillage, conservation tillage, minimum, conservation tillage, maximum. If you have minimum conservation tillage, that's 30% residue. Conservation tillage does not tell you what kind of tillage implement you're using. It only tells you how much residue is left. So if you no-till cotton, and then you no-till cotton, and then you no-till cotton, that is actually conventional tillage because you will not have a 30% residue cover. If you no-till cotton and then plant a wheat cover crop in between, and then no-till cotton the next year, that will be a conservation tillage situation. You could do light disking on a very heavy corn crop and maintain 30% residue, and that would be conservation tillage. There aren't many folks in North Carolina who can actually develop an 80% residue, although some folks are trying, and certainly this is a situation that many people, and particularly NRCS, would like to get farmers to. So this is a screenshot of the phosphorus loss assessment tool. It's going to look a little bit different in the near future because we are bringing the North Carolina Agricultural Nutrient Assessment Tool, which has PLAT, NLU and PLAT, into the nutrient management software. But you'll see a version that doesn't look too dissimilar from this. Once you select your crop, you will be asked to select your tillage type, either conventional tillage, conservation tillage, minimum residue, and remember that's 30%, or conservation tillage, high residue. Now obviously if you have pasture or you have hay, you won't be asked for any kind of tillage. Best management practices, as we saw, can be used in PLAT. They're only used for the portion of PLAT where there is erosion. We don't use conservation practices in trying to reduce soluble P because basically they're not effective. We don't really have any conservation practices for the leaching of phosphorus. And again, buffers can be used when we lose some of our source P. But let's look at the conservation practices we do have and think about how we can use them in phosphorus. So we have buffers, we have water control structures, we have sediment basins, and we have ponds. If you have a buffer, if you have a conservation practice, you'll select from this list. You'll select the conservation practice you have, hit the right button, and that conservation practice will be moved into the selected BMPs, and then you hit OK. You can add more than one conservation practice at a time. But you need to make sure those conservation practices really are going to capture runoff from soil, not runoff, but soil erosion from your field. So how far downstream can a pond exist and still claim credit as BMP and PLAT? The pond must intercept the overland flow, and it must be between the source and the perennial water. Flowing and standing water year-round are considered perennial streams. So in this case, we're obviously not going to have much sediment loss because it's a pasture. You can see that the slope is such, this pond was put in a low portion of the topography, that all of the water is going to be flowing in here. So this pond could be credited in PLAT. If the drainage direction is dissimilar, if it's not flowing into the pond, then you cannot give it credit. Now, one of the interesting things about NRCS is that sometimes they have conservation practices planned that aren't yet implemented. And if they are planned but not yet implemented, they can get credit. So for instance, if you have planned a buffer but it's not implemented yet, you can give it credit. The only exception to this is if your producer has an NPDES permit, and there are very few of those in North Carolina these days. We talked about that in our second or third discussions. You cannot credit planned conservation practices. You can only credit those that have already been implemented. So again, in this particular field, what we're trying to show is there's a tiny little buffer here, but the producer has already made arrangements with NRCS to put in more trees and extend the buffer out, and then that buffer would get credit in this field. How wide should the buffer be? Well, first of all, you need to make sure it's a real buffer. So it can have trees, shrubs, vine, grass, or forbs. But the most important thing to see here, is sheet flow. You must have sheet flow through the system Otherwise, it can't count as a buffer. We don't care what the vegetation looks like. It can be trees next to the stream and grass next to the trees. It can be all trees. It can be all grass. It can be all shrubby, viney materials. Again, it must, however, have this sheet flow. Subdivided field areas that don't drain through a buffer shouldn't be given credit. But in most cases, people do not subdivide fields to run plat or to do their nutrient management planning on. Buffer widths can be really tricky because buffers often are irregular. So how do you figure out what the width is? Well, you can just average the buffer width. If you have a triangular buffer, which is not too frequently, you simply take the midpoint of the widest point of the triangle and you consider that the width of the buffer. If it's a regular shape, you can divide it into segments and average it. Keep in mind that buffers don't get any credit over 100 feet, so beyond 100 feet, there's no value in trying to average the buffer. So let me show you some diagrams of what we're trying to talk about. This is the field. This is the triangular buffer. At its widest point, it's 100 feet. So you simply divide it by 2, and so your average buffer width for this entire field is 50. Here's another field. It's 3 acres in size. You have some buffers that are 100 feet. You have some buffers that are 10 feet. 100 feet plus 35 feet plus 100 feet plus 10 feet divided by 4, and you get 61 feet total average width. Whoops, I can't draw too well. And so you need to do the best job you can averaging these buffers. But again, keep in mind that above 100 feet, you don't get any additional credit. So the question is this an effective buffer? I mean, you have a wide buffer, so you've got a lot of width there, but we're looking for sheet flow. If you look in through here, it's very obvious that you have concentrated flow. You can see from the soil that's piling up here that you have concentrated flow. You can see from the junk that's piling up here that you have concentrated flow. You cannot count this buffer because it is a non-effective buffer. So just because you have a buffer there doesn't mean you automatically get credit. You must look at your buffer to make sure you're getting sheet flow. Again, same example, but you can see this a little bit better. You're getting the junk piling up. You're getting concentrated flow along this pathway. This buffer does not get credit. People have asked, well, if I've got two adjacent fields, and they go into a buffer, does my upper field get buffer credit? And the answer is absolutely yes. So the question is asked, does a buffer have to be immediately adjacent to the field? Can only this field get credit? The answer is no. And again, this field that's adjacent to the field that's adjacent to the buffer gets credit for the buffer. So keep in mind that stacked fields can get credit. Can wetlands receive credit as part of the buffer practice? I want to say that you should all be very wary of giving credit for wetlands. Unless you're a wetland specialist and you know what kind of wetland you're dealing with, you may not be able to make a determination, because if the wetland is connected to perennial waters, you cannot count it as a buffer credit. And if it's just a depressional wetland and it's part of a buffer, then it functions as a pond and it can get buffer credit. But I think it's very difficult to determine this, and so I just give you a lot of caution when trying to determine whether a wetland is part of a buffer. In general, I would be cautious and say no. Here's just a picture of a buffer that that's connected to a wetland that then feeds into a perennial water resource, and so you could not count this. For plat, you have to do soil sampling, and there are some specific criteria that you need to use. When we're discussing soil sampling, and Dr. Krause has already gone through this in a previous session, for pasture and turf, we tell you to use a 4-inch sample. For conservation tillage, we tell you to use a 4-inch sample. And for field crops that are conventionally tilled, we tell you to use an 8-inch sample. The same thing is true in plat. You have to use a 4-inch sample for pasture, hay, turf, and conservation tilled fields. And for field crops that are conventionally tilled, it's 8 inches, I'm sorry. Soil sampling. Again, as Dr. Krause discussed, you should not sample for more than 20 acres at a time. And again, you need to match your soil sampling with your nutrient management plan. So if you're only sampling for 20 acres, then your nutrient management plan needs to be for 20 acres. The good news is that we have very few fields in North Carolina that are greater than 20 acres. There are some, but even when you get down east where you have very large flat areas, almost all of those fields are subdivided by ditches, and each of those fields between the ditch would be considered its own field. You need to sample 15 to 20 cores for the area that you're sampling, and if you have textural changes like you see down here, you may want to sample that differently. But again, this is your judgment call. Not only are you soil sampling for plat, but you're also sampling as part of your nutrient management plan. So you will have a box that asks you to put in your soil test. Excuse me, let me move this back. Because you said that you were doing a conventional tillage in your field, it's automatically going to tell you that your soil sample should be pulled from the 0 to 8-inch depth. If this had been conservation tillage, it would have said 0 to 4-inch depth. Because we're dealing on a soil mapping unit that has the potential to leach phosphorus, so we're in the coastal plain, this box 28 to 32 inches is going to show up. And you're going to have to sample at that 30-inch depth. It's not very easy to sample 28 to 30 inches, so we're going to give you a little primer on how to do that. Oh, so here's this, the 30-inch sample depth will automatically be showing up. I didn't realize I had that slide. And so here's the primer quickly on how to collect these deep soil samples. First of all, it would be advantageous for you to get the fact sheet on this. What you're going to have to do is core down to about 28 inches. Make sure you clean all of the soil out because you don't want any soil from the surface contaminating your deep soil sample. Pull your sample from that 30 to 32 inch area, and we're asking for 10 samples per field. That is a lot of work and it's very difficult, but it's incredibly important. If you don't have that number, you cannot proceed with your plat analysis. Nutrient application rates. When you estimate the nutrient application rates in plat, you basically already have to have written your nutrient management plan. It's kind of a chicken-egg thing. You're putting typically your nutrients on at a nitrogen rate. And so, for instance, if that nitrogen rate requires that you put on, let's just say, 3 tons of litter to meet your nitrogen expectation, then you will be putting on 3 tons of litter that has, on average, 35 pounds of P in it, or 100 pounds of phosphorus. And so you have to put in plat that you're using 3 tons of litter or 100 pounds of phosphorus. So again, it's a bit of a chicken-egg thing. Also, the phosphorus content of your litter should come from your own records. They are much, much better than book values. I would always recommend you to put in your own values. There are book values in plat. They're older values. They're probably higher than current values. But since you have to have waste analysis reports for your nutrient management plan, again, I can't stress strongly enough that you use the phosphorus concentrations in your own animal waste. One of the last areas that we're going to talk about is drainage spacing. And this is going to be for those of you working in the coastal plain area. The real question is, when and how should drainage be computed? Each of you is going to pull up a soil mapping unit for the field that you have. And if that field has the potential to be drained, you will be asked automatically in the program to enter the distance between drains, either drainage tiles or drainage ditches, in feet, and you will be asked the depth of those drainage ditches or tile in inches. Typically, these drains are regularly spaced, and that's really easy. Sometimes they're not. So it's the irregularly spaced drains that we have to spend some time talking about the calculations. So again, this is the Belhaven muck that I talked about earlier. It is a soil that can be drained. If you had this box automatically comes up, it asks you if it's drained or not. If it's not drained, you click no. This box will go away, and you do not have to enter the drain spacing in feet or the drainage depth in inches. This is a regularly spaced drain system. Typically, these drains are spaced at 300 feet, and the drainage depth is 36 inches. This is the really simple part of drainage. So again, 300 feet between the center rows, very easy to determine. It gets trickier when, for instance, you have just one drain. For instance, sometimes people will put one tile drain in a field, or they'll put one ditch in a field. Now, let me say that if on this field, if you're dealing with this field, and right here's the drainage ditch, I'm sorry, not the drainage ditch, the tile drain, you would only calculate the amount of land that is drained by that tile line, which means that you would have to conduct your nutrient management plan separately on the parts of the field that were not drained. So this would be one nutrient management plan, and there would be a separate nutrient management plan for this area. I suspect that most planners would not do this because I don't think most farmers would manage these differently. But we want you to know how to do this just in case the producer wants you to do this. So you take the area of the field that's drained, so it's 100 feet long and 8 feet wide. You multiply those two numbers, then you divide by the length, and so the distance is 8 feet. And that's what you put into your drainage width. In fields that are not subdivided, choose the predominant drainage condition. That's just what we talked about. When the entire field is not drained, you're going to have to decide whether subdivision is necessary. And again, if you do subdivide, you'll have to use a separate plat analysis for each subdivision, as well as a separate nutrient management plan, and potentially that farmer will have to do 2 different pieces of management on that field. What about fields that only have 1 perimeter ditch along the edge? How do we figure out that spacing? This situation actually happens quite a bit, and it's not too dissimilar from what we just showed you. So we have a poorly drained soil here. We have this perimeter ditch here. We assume that this area is drained by this ditch. This area is not drained by that ditch. So again, what we would be subdividing this field into Part A, which is not drained, and Part B, which is drained. The calculation is identical to the previous calculation. You calculate the length, multiply it by the width, and then you divide it by the length to get your drainage spacing. So that's it as far as frequently asked questions, but there are a couple miscellaneous things that we'd like to mention. The plat rating is only applicable for as long as the nutrient management plan is, which is at least every 5 years. So you'll have to run your plat rate. You have to determine a new plat rating every 5 years. A plan with plat is good for review, for the review interval, unless something significant changes in the number of animals you have, etc. Dr. Krause talked about those kinds of changes when we talked about some of the regulations required for nutrient management plans. If there's no change in a plan, there's no change, then you don't have to redetermine plat. However, this may be changing, and again, if there's a change in livestock numbers, then you're going to have to redo plat. That's it for now. If you all have any questions, please feel free to email me, and we will see you in class when we do our nutrient management training. Dr. Krause, do you have any comments?
No, I think we're done, and I think this is the last of the sessions, and we hope that you find this training format easily accessible and convenient for you, since you can do it from the comfort of your home or your office. With that, I'm going to stop the recording, and we are done.